Okay, in today's lecture, we're going to finish the last part of the section 6.3 material on Taylor and Maclaurin series. So we had seen last time that we can use the Maclaurin series of a function in order to approximate the value of a definite integral if the function that we're integrating can't be integrated using the other techniques which we've discussed in our course. So as another example of such a problem, we're asked to approximate the definite integral from 0 to 1 of e to the negative x squared with respect to x. In our approximation, it needs to have an error of less than 1/1000th. So this is another example of a function, this integrand, e to the negative x squared, which cannot be integrated using any of the techniques which we've discussed in our course. But we could make use of a power series representation of that function in order to integrate this and then approximate this definite integral as the sum of a series. So here we see that our integrand involves an exponential, e to the negative x squared. So we might start by considering the Maclaurin series for e to the x. So let us recall that the Maclaurin series for e to the x was given by the sum from n equals 0 to infinity of x to the nth power over n factorial. So if we want a Maclaurin series for e to the negative x squared, we would simply replace x with x negative x squared in our Maclaurin series. So we have negative x squared to the nth power over n factorial, which we can then rewrite as the sum from 0 to infinity of negative 1 to the n times x to the 2n over n factorial. So then, if we want to evaluate the definite integral from 0 to 1 of e to the negative x squared with respect to x, that is the integral from 0 to 1 of the sum from 0 to infinity of negative 1 to the nth x to the 2n over n factorial with respect to x. So integrating term by term, we would have the sum from 0 to infinity of negative 1 to the nth over n factorial, and the antiderivative of this x to the 2n term with respect to x gives us x to the 2n plus 1 divided by 2n plus 1. And we are evaluating from 0 to 1. So substituting 1 in for x, we have the sum from 0 to infinity of negative 1 to the n over n factorial times 2n plus 1. And then we subtract what we get when we plug in 0 for x. But since this is a Maclaurin series, it's centered at 0, and plugging in 0 for x gives us 0. So we have the following expression for the sum of our series. It's represented for our definite integral. It's given by the sum of this alternating series. So we can approximate the sum of an alternating series by using an nth partial sum approximation. And the question is, well, how many terms do we need to add for this series in order to achieve an approximation which has an error of less than 1/1000th? So since this is an alternating series, we can make use of the remainder estimate for the alternating series test. So let's say by the remainder estimate for alternating series, we know that the error in our nth partial sum approximation would be the absolute value of the remainder, r sub n, and this is bounded above by a sub n plus 1. That is the n plus 1 term of our series. So in this example, a sub n plus 1 will be 1 over n plus 1 factorial times 2n plus 3. So in order to achieve the desired accuracy, we're going to take this expression for the maximum possible error, 1 over n plus 1 squared times 2n plus 3, and let it be less than the desired accuracy, which was 1/1000th. Now to solve for n, we can take the reciprocal of both sides, and we find n plus 1 factorial times 2n plus 3 has to be greater than 1000. In testing integer values of n, we find the smallest integer value of n for which this inequality is satisfied is 4. So we need the sum of the first several terms up through n equals 4. So here, the definite integral that we were given from 0 to 1 of e to the negative x squared dx is approximated by the sum of the first several terms up through n equals 4. So looking at our series here, which is the definite integral, we would start with the term n equals 0 for our first term, and if n equals 0, we have 1. Then if n equals 1, we have negative 1 over 3. If n equals 2, we have a positive 1 over 2 factorial times 5. If n is 3, we have a negative 1 over 3 factorial times 7. And if n is equal to 4, we have a positive 1 over 4 factorial times 9. So this sum of the first few terms of our series up through the value where n is equal to 4 would be an approximation for the value of this definite integral, and it is accurate to within 1/1000th. Okay, so our last couple of examples have illustrated that we can use Maclaurin series to find the value of a definite integral as the sum of a series. And if we need to approximate the sum or that definite integral within a given accuracy, we can use an nth partial sum approximation by looking at the remainder estimate and determining how many terms we need for the desired accuracy. Now, another application of Taylor and Maclaurin series is that they allow us to find the sum of certain types of series if we can think about them as a Maclaurin series. So let's look at some examples. In this first example, we are asked to find the sum of the series from 0 to infinity of negative 1 to the nth times 3 to the nth times x to the 2n all over n factorial. So if we start by rewriting this series a little bit, let's think about how we could maybe simplify this. So we could rewrite this as the sum from 0 to infinity of negative 1 to the n times 3 to the n, and our x to the 2n power I can think of as x squared to the nth power. And then the whole thing is being divided by n factorial. Now, using properties of exponentials, if I'm taking the product of 3 terms, which are all being raised to the nth power, that is the same as taking the product of those 3 terms, that is negative 1, 3, and x squared, or negative 3x squared, and then raising that product to the nth power. And then we're dividing the entire thing by n factorial. Now, at this stage, we start to see that this is similar, or looks similar, to the Maclaurin series for the exponential function. So in particular, let us recall that e to the x power is given by the sum from 0 to infinity of x to the nth over n factorial. So that looks very similar to the series that we had here. The only difference is instead of just having x to the nth, we have negative 3x squared to the nth. So, if we think about this in terms of a Maclaurin series, the summation which we have can be thought of as the Maclaurin series for e to the negative 3x squared. So that would be the sum of this given series. By rewriting it, we saw it was the Maclaurin series for a function in terms of e to the x. So let's look at another one. In part B, we have the sum from 0 to infinity of negative 1 to the nth times pi to the 2n plus 1 over 3 to the 2n plus 1 times 2n plus 1 factorial. So again here, if I make use of properties of exponentials, I can rewrite this in a simplified way. So let us look at these two terms. We have pi to the 2n plus 1 divided by 3 to the 2n plus 1. So, making use of properties of exponentials, I can rewrite that as pi divided by 3 and then raise that quantity to the 2n plus 1 power. And then the terms that I'm left with were negative 1 to the n divided by 2n plus 1 factorial. So we see that this looks somewhat similar to the Maclaurin series for the sine function. If we recall, the Maclaurin series for sine x is given by the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. So that looks exactly like what we have here. The only difference is instead of x to the 2n plus 1, we have pi over 3 being raised to the 2n plus 1. So replacing x by pi over 3 in our Maclaurin series, we have the summation that we're interested in. Is given by sine of pi over 3. And sine of pi over 3 is root 3 over 2. So in these last two examples, we're seeing that we could find the sum of a series, which in almost all of our examples we cannot do unless we have a telescoping or geometric series. Or we're seeing here, if we can think about our series in terms of a Maclaurin series, we might be able to find its sum. So let's look at some other ones. In part C, we have the sum from n equals 1 to infinity of negative 4 to the nth times x to the 2n times n factorial. So if we rewrite this a little bit, we have the sum from n equals 1 to infinity of negative 4 to the nth, and then our x to the 2n can be thought of as x squared to the nth all over n factorial. So what we have is the sum from n equals 1 to infinity of negative 4x squared quantity to the nth over n factorial. And again, this looks very similar to the Maclaurin series for e to the x. So let us again recall that e to the x is the sum from 0 to infinity of x to the n over n factorial. So that's almost exactly what we have here. We have this x to the nth being replaced by negative 4x squared to the nth. And then our summation is starting at a different index value. Instead of starting at n equals 0, we see here that our initial term corresponds to n equals 1. So if we want to make use of the Maclaurin series for e to the x, we need to rewrite this series so that its initial term corresponds to 0. So if we were to force this to start at n equals 0, let's see how that would change our series. So by including the 0 term, I would have included one extra term in my summation. Let's see what value. When I plug in 0 for n, I have negative 4x squared raised to the 0, or 1, divided by 0 factorial, which is 1. So by including the index value n equals 0, I've added 1 to the sum when I only started at 1. So in order to keep these values equal to each other, I then have to subtract 1. And now, this initial series that I have, which starts at n equals 0, is the same as the Maclaurin series for e to the x, but where x has been replaced by negative 4x squared. So I have e to the negative 4x squared minus 1 as the sum of this series. Okay. Now, in the last part of this section, we're going to talk about something called a Taylor polynomial, which is a polynomial approximation of a function. And the reason that we might be interested in approximating a function by a polynomial is that polynomials are pretty easy to work with. We know they're easy to take derivatives of, integrals of, limits of. So having a polynomial approximation of a function, which is a little bit difficult to work with, is often very useful in some applied problems. So let's start by defining what is called a Taylor polynomial. So let us suppose that a function f of x has a Taylor series centered at a, given by the following. So f of x could be represented as a power series centered at a, where for our Taylor series, the nth coefficient is given by the nth derivative of our function at x equals a divided by n factorial. So if we want to approximate the sum of a power series, we could use an nth partial sum approximation. So here the nth partial sum of a Taylor series is an nth degree polynomial called the Taylor polynomial for that function f of x at x equals a. So this Taylor polynomial is denoted as t sub n of x, so the nth degree polynomial. The subscript denotes what degree we're working with. And if we were to write out the first n, or the sum of the first n terms of our Taylor series, well, when n is equal to 0, we have f of a, then the derivative of f at a times x minus a to the first, then the second derivative, f double prime of a over 2 factorial x minus a squared, the third derivative of f at x equals a over 3 factorial times x minus a cubed, and so on until we get to the nth term. The nth derivative of f at a divided by n factorial over x minus a to the nth power. So this nth degree Taylor polynomial can be used to approximate the value of the function f of x. So let us consider an example of this. Suppose that we want to find the third degree Taylor polynomial for the square root function at a equals 4. So if I want a third degree Taylor polynomial approximation, let's think about how many derivatives I'll need to find here. So in general, the nth degree Taylor polynomial, we take the sum of all these terms up through the nth derivative of my function. So when we're asking for a third degree Taylor polynomial, I need the first 3 derivatives of this function. So in this example, we have f of x is the square root of x, or x to the 1/2 power. So its derivative, f prime, is then 1/2 x to the negative 1/2, or 1 over twice the square root of x. Our second derivative, f double prime, is then negative 1/4 times x to the negative 3/2 power, or negative 1 over 4 times x to the 3/2. And finally, for our third derivative, f triple prime of x, we have a positive 3/8 x to the negative 5/2 power, or 3/8 divided by x to the 5/2. Now, since we are centering this Taylor polynomial at the value a equals 4, we need to evaluate our function and each of these first several derivatives at that value of a, in this case 4. So we find our original function, f of 4, is the square root of 4, or 2. F prime of 4 would be 1 over 2 times the square root of 4, so 1 over 2 times 2, or 1/4. F double prime of 4 is given by negative 1 over 4 times 4 to the 3/2, which would be the same as 4 to the 1/2 cubed, or 2 cubed, which gives us 8. So altogether, negative 1 over 32. And our third derivative of f at x equals 4 is given by 3/8 divided by 4 to the 5/2, or 2 to the 5th. 2 to the 5th would be 32. So we have 3 over 8 times 32, which leaves us 256. So now that we have these terms, we're ready to find our third degree Taylor polynomial. It's denoted as t sub 3 of x. The subscript 3 denotes that it's the third degree Taylor polynomial. And let's look at the terms that we're summing here. Our first term is f of a. In this case, f of 4 was found to be 2. Then our next term is f prime of a, which was 1/4, times x minus a, which was 4, to the first power. Then our next term, we have f double prime of a, which was negative 1 over 32, but then we have to divide by 2 factorial, or 2. So negative 1 over 32 divided by 2 gives us negative 1 over 64 times x minus 4 squared. And in our last term, we have the third derivative evaluated at a, which we found to be 3 over 256, and then we divide by 3 factorial, or 6. So let's see what we have here. To show my work a little bit, I would have 3 over 256 over 3 factorial, which is 3 times 2 times 1, times my x minus 4 to the third power. So to simplify this last coefficient, let's see what we have. So here I see that I could cancel a factor of 3 on top and bottom, and I'm left with 1 over 256 divided by 2, or 1 over 512 times x minus 4 to the third power. So this is a third degree polynomial, which would be an approximation of the square root of x for values of x that are close to 4. So let's look at how accurate a Taylor polynomial approximation of a function might be. So anytime that we're using an approximation of something, we of course want to ask how good our approximation is, or what is the error in our approximation. So to answer that question, we're going to define a remainder for a Taylor polynomial approximation of a function. So if we use an nth degree Taylor polynomial, t sub n of x, to approximate a function f of x at x equals a, then the remainder of that approximation, which is a function of x, we will call it r sub n of x, is the difference between the actual value of our function f of x and its nth degree Taylor polynomial. So the question becomes, well, how good is this approximation? Or if we need to have accuracy within a desired range, how large should we take in? That is, how many terms of the Taylor series do we need to add in order to achieve a desired accuracy for a function? Now, both of those questions can be answered making use of a result known as Taylor's inequality. So let's look at what Taylor's inequality says. It says that the error in our approximation, which would be the absolute value of this remainder, is bounded above by capital M over n plus 1 factorial times x minus a to the n plus 1 power, where this expression capital M is the largest value of the absolute value of the n plus first derivative of our function for values of x that are within r units of a. So whenever we're using Taylor's inequality, usually our first step will be to find this value capital M. What is the largest possible value of our n plus 1 derivative on the interval that we're considering? So let's look at another example working with Taylor polynomials where we'll make use of Taylor's inequality. So let's suppose that we have the function natural log of x, and we want to approximate this function using a third degree polynomial. So we're told here to find the third degree Taylor polynomial for log x at a equals 3. So as with our last example, since we want a third degree Taylor polynomial, we're going to find up through the first 3 derivatives of our function. So here f prime of x is 1 over x, or x to the negative first. The second derivative, f double prime of x, would be negative x to the negative 2, or negative 1 over x squared. And our third derivative, f triple prime of x, is positive 2x to the negative third, or 2 over x cubed. So evaluating each of these derivatives at our centering point, a equals 3, f of 3 is natural log 3, f prime of 3 is 1/3, f double prime of 3 is negative 1 over 9, and our third derivative evaluated at 3 would be 2 over 27. So at this stage, we're ready to find our Taylor polynomial. The third degree Taylor polynomial, t sub 3 of x, is given by f of 3, which was log 3, plus f prime of 3, which was 1/3, times x minus 3 to the first power, plus the second derivative, f double prime of 3, which is negative 1/9, divided by 2 factorial, times x minus 3 squared, and then plus our third derivative, 3, which was 2 over 27 over 3 factorial, times x minus 3 cubed. So let's simplify these coefficients a little bit. Our first two terms aren't so bad. We have log 3 plus 1/3 of x minus 3. And then minus, let's look at how we can simplify this coefficient. We have 1/9 divided by 2 factorial, or 2. So 1/9 divided by 2 gives us 1/18 times x minus 3 squared. Plus, let's look at this last term. So we have 2/27 divided by 3 factorial. Now recall 3 factorial is 3 times 2 times 1. So if I cancel my factor of 2 in the numerator with this factor in the denominator, I'm left with 1 over 27 divided by 3, or 1 over 81 times x minus 3 to the third power. So this would be the third degree Taylor polynomial for the natural log of x centered at a equals 3. Now in part B of this example, we're asked to use Taylor's inequality to estimate the accuracy of the approximation of our function by its third degree polynomial that we found in the previous part, if we're restricting ourselves to the x interval from 2 to 4. So recall what Taylor's inequality says. Taylor's inequality says that our error, which is the absolute value of r sub n of x, the remainder of this approximation, is bounded above, that is, it's less than or equal to, capital M over n plus 1 factorial times x minus a. In this example, a was 3. We were centering our Taylor polynomial at 3, raised to the n plus 1 power, where m is the largest value of our n plus first derivative on the interval that we're considering. So if we're looking at a third degree Taylor polynomial approximation, that is t sub 3 of x, then our value of n is equal to 3. So the first thing that I want to do for Taylor's inequality, I had mentioned, is find this value of capital M. So in order to find capital M, I'm going to need to look at the n plus first, or if n was equal to 3, the fourth derivative of my function. So using our work from the previous problem, let's say by part A, we had already found the third derivative, f triple prime of x, of this function to be 2x to the negative third, or 2 over x cubed. So our fourth derivative of this function is given by negative 6x to the negative fourth, or negative 6 divided by x to the fourth power. Now to find m, we're supposed to look at the absolute value of that quantity. So let's consider the absolute value of this fourth derivative. That is the absolute value of negative 6 over x to the fourth, which would be positive 6 over the absolute value of x to the fourth power. Now to find the value of m, we want to make that quantity as large as possible. M is the upper bound for that quantity. So to maximize this expression, 6 over the absolute value of x to the fourth, we want to divide, or we want to make x as small as possible. So to maximize the value of a fraction, we want our denominator to be as small as possible. Now, the smallest value of x that we have on the interval that we're considering is x equals 2. So the upper bound for this expression would be 6 over 2 to the fourth power, which is 6 over 16, or 3 over 8. So this is our value for m that we're going to use in Taylor's inequality. So applying Taylor's inequality, we have the error in our Taylor polynomial approximation is given by the absolute value of our remainder, r sub 3 of x, since we were using a third degree Taylor polynomial. And this is bounded above by m, which was 3 over 8, divided by n plus 1, or in this example 4, factorial, times the absolute value of x minus a, which was 3, raised to the n plus 1, or the fourth power. So let's simplify this coefficient out in front. We have 3 over 8 divided by 4 factorial, which is 4 times 3 times 2 times 1. So to simplify that ratio, I could cancel a factor of 3 on top and bottom, and I'm left with 1/8 divided by 8, or 1 over 64. So we have 1 over 64 times the absolute value of x minus 3 to the fourth. And I want to know, well, what is the worst case error that I could have? What is the maximum value that this error could take? So in order to maximize this expression, I want to maximize the absolute value of x plus 3 to the fourth. So here, the largest value that I could have for the absolute value of x minus 3 is 1. Now, why 1 here? So let's look at this. This quantity, absolute value of x minus 3, denotes the distance that I've moved from 3. So on the interval from 2 to 4, we can move at most 1 unit away from 3. 3 is right in the middle of that interval, so I could move 1 unit to the left or 1 unit to the right. So by plugging in either x equals 4 or x equals 2, I would have, say, 4 minus 3 to the fourth power in absolute value. So 1 to the fourth, or if I plugged in if I plugged in x equals 2, I would have negative 1 to the fourth power, which is still 1. So the largest value for our error is 1 over 64. So what we're saying here is that I can approximate my function f of x, which, recall from part A, was the square root of x, by that third degree Taylor polynomial that we found in part A, and in the x interval from 2 to 4, that is, if I'm only plugging in values of x from 2 to 4, this approximation will have an error of at most 1 over 64. So in our last example, let's look at a more practical application of Taylor's inequality. So in this next one, we are asked to determine the degree of the Taylor polynomial of the function f of x equals log of x plus 1 centered at 0, such that approximating our function by that nth degree Taylor polynomial will have an error of less than 1/100th on the interval from 0 to 0.1. So in order to apply, or as soon as we see that this problem involves the error involved in a Taylor polynomial approximation, we know we want to use Taylor's inequality. And to use Taylor's inequality, we need to find that value capital M. That is the upper bound on the n plus first derivative of our function. So my first step here is to find an expression for the n plus first derivative of my function. So let's look at our function. Here it is the natural log of x plus 1. So our first derivative, f prime of x, is given by 1 over x plus 1. Or, if we prefer to think about this, x plus 1 to the negative first. So then our second derivative, f double prime of x, would be negative x plus 1 to the negative 2, or negative 1 over x plus 1 squared. Then our third derivative, f triple prime, is positive 2 times x plus 1 to the negative third, or 2 over x plus 1 quantity cubed. So let's look at another one. Our fourth derivative, after this I think we can see the pattern emerge. The fourth derivative would be negative 3 times 2 times x plus 1 to the negative fourth, or negative 3 times 2 over x plus 1 to the fourth power. So let's see if we can find an expression in general here. So in general, if we're looking for the nth derivative of a function, of our function, f of x, let's look at the pattern that seems to be emerging. So let's start with our denominator and see if we can find the pattern. For the first derivative, f prime, our denominator was x plus 1. For the second derivative, our denominator was x plus 1 squared. For the third derivative, we had x plus 1 cubed. And for our fourth derivative, we had x plus 1 to the fourth. So we suspect then that for our nth derivative, our denominator would be x plus 1 to the nth power. The power in the denominator is the same as the order of our derivative. Now let's look at the numerator, the constant in our numerator. For our fourth derivative term, we had 3 times 2. For the third derivative, we had 2, or 2 times 1. For the second derivative, we just had a constant of 1. And for our first derivative, again, we had a constant of 1. So we can think of this constant in our numerator as being a factorial term. And we see the following pattern. For our fourth derivative, we had 3 factorial. For our third derivative, we had 2, or 2 factorial. For the second derivative, we had 1, which was 1 factorial. So our numerator is always the factorial of the constant which is 1 less than the order of our derivative. So for the nth derivative, we would have n minus 1 factorial. Now the last thing that we still have to capture is the alternating sign. Notice that our first derivative was a positive expression. Our second derivative was a negative. Our third derivative was positive, our fourth derivative was negative, and this pattern will repeat. So to capture an alternating sign, we're going to have negative 1 to some power, and let's think about which terms we want to be positive. So here our first derivative, our third derivative were both positive, so the even terms are going to be negative. So let me take, for my power of negative 1, n plus 1, so that if n is an even integer, I have an odd power of -1, and I get a negative for those terms. So we found an expression for our nth derivative, but recall for Taylor's inequality, I need the n plus 1 derivative in order to find that value of m. So if we replace n by n plus 1 in the expression that we just found, we would have -1 to the n plus 2, which is the same as -1 to the nth, times n factorial all over x plus 1 to the n plus 1 power. So I mentioned here our -1 to the n plus 2. We can think of that as -1 to the nth times -1 squared, which is just 1 times n factorial over x plus 1 to the n plus 1 power. So now that we have our n plus first derivative, we can try to find the value of m. If we consider the absolute value of this n plus 1 derivative, then we have the absolute value of -1 to the n times n factorial over x plus 1 to the n plus 1 power. Or, this is the same as positive n factorial over the absolute value of x plus 1 to the n plus 1 power. Now again, to make this quantity as large as possible and find the value of m, we want to divide by the smallest value possible. So to minimize the value of x plus 1, we want to choose the smallest value of x on the interval we're considering. Here, our interval was from 0 to 0.1, so the smallest value of x would correspond to 0. So we would have, for our denominator, 1 to the n plus 1 power, which is just 1. So that leaves us with an n factorial for the value of m. So once we have m, we're ready to apply Taylor's inequality. So let's see what we have. By using Taylor's inequality, the error in a Taylor polynomial approximation is bounded above by m, which we found to be n factorial, divided by n plus 1 factorial, times the absolute value of x minus a. In this case, we were told we were centering at 0, so x minus 0 to the n plus 1 power. So simplifying this expression, well, n factorial divided by n plus 1 factorial leaves us 1 over n plus 1, and then we're multiplying by the absolute value of x to the n plus 1 power. Now, on our interval, we want to know what the worst possible error could be. So in order to maximize this expression, we would want to take the largest value of x possible on our interval. Recall here our interval was from 0 to 0.1, so the largest value of x is 0.1 or 1/10. So to make this error as large as possible, we would have 1 over n plus 1 times the absolute value of 1/10, which would be 1/10 to the n plus 1 power, which I could rewrite as 1 over n plus 1 times 10 to the n plus 1 power. Now, to achieve the desired accuracy, I'm going to take the expression that we just found for the worst possible error and make sure it is less than the error bound that we're given. So looking back at our problem statement, here the error bound that we were given was that we need it to be less than 0.01 or 1/100th. So to ensure that, we take the maximum error and let it be less than the error bound that we're given. So it follows that by taking the reciprocal, we have n plus 1, 10 to the n plus 1 would have to be greater than 100. And we find that in order for this inequality to hold, we need n to only be 1 or greater. That is, I need the first degree Taylor polynomial or a higher degree Taylor polynomial in order to approximate this logarithmic function on that interval such that we have accuracy to within 1/100.